Welcome to this online training about high-performance memory interfaces in Intel Agilex devices. My name is Steve. This training is available for desktop viewing as well as in a format compatible with portable devices, both available from the same link included in your registration email. For either version, while watching the training, use the controls at the bottom and side of the screen to navigate to any point. Feel free to pause the training at any time to experiment with the software. When you are done with the training, please use the link provided in the registration email you were sent to provide us feedback on the training and ways in which it can be improved. I'll remind you about that later. The main objective of this training is to get you familiar with the parallel external memory interface options available in Intel Agilex FPGA devices and how to implement them in your designs. You'll learn about the architectural features available in Intel Agilex devices that implement memory interfaces. The architecture is different from previous device families, so it's important to understand the underlying architecture to see how everything works and how external memory interfaces are built. You'll then get familiar with the design flow for the memory IP for new devices called Altera EMIF FM. This includes simulation, timing analysis, and using debug tools to verify the correct operation of an interface. Here is the full agenda for this training. This final part discusses how to use the available on-chip debugging tools to verify or debug a memory interface while it is running on a board. As mentioned, when you registered for this training, it is highly recommended that you have previously watched the first online training listed here, or have experience with implementing external memory interfaces in other FPGA devices. The first online training linked here goes into detail on the basics of external memory and implementing memory interfaces in older devices that use the UniPHYIP IP and the high-performance memory controller. The second linked training discusses memory interfaces in Intel Cyclone 10, Intel Aria 10, and Intel Stratix 10 devices. It builds on the information presented in the first training. There are some similarities in the EMIF implementation between the Series 10 devices and Intel Agilex devices, but the architecture and capabilities are different enough that this training is your best resource for an Intel Agilex implementation. For more detailed information about all aspects of the memory IP and implementing a complete memory interface, see the External Memory Interfaces Support Center and the Memory IP user guides available there for each device family. It's a good idea to always have the EMIF IP user guide for your targeted device available. They are the definitive guides for every aspect of creating a memory interface using an Intel FPGA and will be referenced throughout the training. Once again, here is the recommended design flow for creating a working EMIF interface. In this section of the training, we'll look at your options for performing on-chip verification and debugging, allowing you to debug the design while it's running in hardware. Let's start by looking at what tools are available and the basics of how to use those tools to debug an interface. There is a lot to take into consideration when designing and building an external memory interface, some of which has been covered in the previous parts of this training. While it may seem daunting to verify and debug, many support resources and tools are available to help you with the process. The EMIF IP user guide should be your starting point. The document breaks down the different areas where you might be having issues and provides recommendations for how to verify and solve problems. It also includes a handy debugging checklist to help you keep track of the process. The main areas of concern and general recommendations are listed here. The fact that most of the interface is hardened but customizable through IP parameter settings helps the design and verification process. So in most cases, you would want to focus on your user logic that connects to the IP, as well as the board design. Even board design issues can, in some cases, be overcome through adjustments to IP parameters, avoiding a costly board respin. In this part of the training, we'll focus on the tools you can use while the design is running in hardware to help you identify and solve issues found in the areas listed. As with the memory IP in previous device families, on-chip debugging tools are available to help debug problems with Intel Agilex memory interfaces and analyze an interface's operation during runtime. The tools we'll discuss are listed here. The Signal Tap Embedded Logic Analyzer is a great tool for examining internal signal levels when a set of defined conditions, called a trigger, occurs. To learn how to set up and use Signal Tap, see the online training linked here. In this section of the training, we'll briefly look at the signals to tap with Signal Tap, and then focus on how to use the EMIF Debug Toolkit and the new 2.0 version of the traffic generator with one or more memory interfaces implemented using the Altera EMIF FM and Altera EMIF Cal IP. Before we look at the debugging tools specifically designed for testing an external memory interface, let's look at the signals that are useful for examination with the Signal Tap Embedded Logic Analyzer. As with other high-performance IP, Signal Tap should only be used to tap lower-speed internal signals instead of signals on the I/O. In this case, the local interface between the user logic and the controller is the most common interface to tap. This is an Avalon memory-mapped interface with all the signal names prefixed with AMM. Other signals to tap are listed here. The local cal signals indicate the success or failure of the calibration performed by the I/O SSM block. The local reset signals indicate when the user logic requests the interface to be reset and when the interface comes out of reset, ready for normal operation. You can check to see when the memory IP is being properly clocked based on the status of PLL locked. Finally, if you are using the traffic generator IP as your user logic, the traffic gen signals indicate whether the writes and subsequent reads performed by the IP were successful. We'll look at the traffic generator in more detail later. Of course, for debugging your own user logic, if you are not using the traffic generator, tap the signals you need to in your own design. Now, let's take a look at how to enable and use the EMIF Debug Toolkit. If you are not familiar with it from previous device families, the EMIF Debug Toolkit is a runtime debugging tool included with the Intel Cortex Prime software that connects to the calibration sequencer of the memory interface through a JTAG connection, making it possible to analyze the results of calibration. This can help in determining why calibration may have failed and what adjustments can be made to fix it. The tool can generate reports on the overall calibration, the settings that were used during calibration, and the detected margin on every data signal in the interface. You can manually perform a recalibration of the interface at any time, or rerun the traffic generator to send customized write and read tests to the external memory. We'll look at this feature later. The tool also gives you the ability to read individual settings selected during calibration, such as on-die termination and pin delay, and adjust each one individually. The EMIF Debug Toolkit is enabled during IP generation. To enable it for a new design with a single memory interface in either the top or bottom row of the device, enable the option shown on the Diagnostics tab of the EMIF IP Parameter Editor and generate an example design as discussed previously. Also, turn on the In-System Sources and Probes setting. If you're not familiar with the standalone version of this tool in the Intel Cortex Prime software, In-System Sources and Probes allows you to actively monitor internal design signals, referred to as probes, and actively control the level or value of signals, referred to as sources. Enabling this option for the example design provides access to a number of useful signals for monitoring and control, and is required for the driver margining feature in the EMIF Debug Toolkit, discussed later. To enable use of the toolkit in an existing design, enable the Add EMIF Debug Interface option in both the EMIF IP and the Calibration IP. enable the ISSP option manually in the .qsf file as shown. This is required because the option in the parameter editor is for enabling the feature in a new example design, not for enabling the option on an existing design. Once everything is enabled, generate the IPs and compile the project. Enabling the toolkit is a little more complicated if you have more than one memory interface placed in either the top or bottom row of the device. Since all interfaces in a row share the same I/O SSM for calibration, the design must take this into account to allow Debug Toolkit access to all interfaces. First, it's recommended to create separate EMIF example design projects for each interface. Set the EMIF IP parameters appropriately for each interface before generating each example design project. Designate one of the projects as the final or main project where the other interfaces will get integrated. Next, for each example design other than the main one, find the .ip files for the EMIF IP, the traffic generator IP if used, and the reset release IP, named ninit_done. Copy these files to the main project's edsynth directory, renaming them in the process to avoid overwriting the main project's EMIF IP. If you've done this correctly, you'll see the IP copies appear in the IP catalog for the main project in Platform Designer as shown. Now, open the main project's Platform Designer system to add the copies to the design. Connect everything together and enable the toolkit for all interfaces. If you don't need assistance with connecting the multiple interfaces to the calibration IP, you can skip ahead to learn how to launch and use the toolkit. To allow toolkit access to multiple interfaces, increase the number of calibration interfaces parameter in the calibration IP. This adds additional EMIF CalBus conduit interfaces to the calibration IP as shown. Connect each of these to an EMIF IP. The ordering of which calibration IP interface you connect each interface to is important because the identifying number of the calibration IP CalBus interface is used as an ID for which EMIF to debug in the toolkit. Also, don't forget to connect the CalBus clock interface from the calibration IP to each of the additional EMIF IP. Export the appropriate interfaces on each of the additional EMIF IP to connect them up outside the system. These include PLL ref clock, OCT control, the external memory I/O connections, and the status interface. While not shown, if you are sharing core or PLL reference clocks between the multiple interfaces, as discussed in an earlier part of this training, you'll need to make additional connections either inside or outside the system. Next, if you are using the traffic generator for any of the additional memory interfaces, make the appropriate clock, reset, and Avalon control interface, if enabled, connections as shown to create the local interface. If you have replaced the traffic generator with your own user logic, the same interfaces on the EMIF IP should be used. Finally, connect the ninit_done interface from the reset release IP to indicate to the traffic generator when device initialization is complete and user mode initialization can begin. The final connections involve the local reset combiner IP. A single instance of this IP is used for either the top or bottom I/O row, like the calibration IP. As such, it should not be copied from one of the additional example design projects if the additional interfaces are located in the same row as the main project. This IP is used to request the reset of a memory interface and to indicate when an interface has come out of reset. To expand its use for additional memory interfaces, increase the parameter values shown despite the warning displayed in the parameter editor. These parameters increase the number of request and status interfaces, which should get connected to each additional EMIF IP as shown. Once you've created project assignments and compiled the project, program the device with the design. Start the system console from either Platform Designer or the Intel Cortex Prime software and launch the toolkit. This involves loading the design, selecting the appropriate I/O SSM instance, either the top or bottom row if both are being used, and starting the toolkit itself. The EMIF IP User Guide has all the details. Once the toolkit is started, select the appropriate memory interface ID based on the CAL bus interface connections to the calibration IP, as discussed earlier. Only one interface can be debugged at a time, so click Deactivate Interface, select a different ID, then click Activate Interface to switch to debugging a different EMIF. Clicking Export Populated Tables writes out .csv files for the data tables available in the Toolkits tabs, discussed next. The EMIF Debug Toolkit is easy to use, with all options and features available organized into the tabs shown. Here's a quick rundown of each tab. The Memory Configuration tab lists the basic parameters that were specified for this interface in the IP Parameter Editor. The Calibration tab lets you rerun calibration a set number of times that you specify. The tab indicates for each iteration if the calibration was successful. You can also run or rerun the traffic generator on this tab and see if default or custom data written to the memory was read back successfully. The Calibration Report tab provides more detailed information about each iteration of calibration that was performed on the Calibration tab. If a calibration failed, the first calibration stage that failed is displayed, along with what data groups caused the failure. The Report tab also includes detailed information on the read and write delays selected by calibration, and the valid delay margining ranges of each DQ, DQS, and DM or DBI pin. It also displays the selected voltage reference value for each data group along with margining ranges. The Calibrate Termination tab displays the on-die termination or ODT settings that were specified in the EMIF IP and allows you to change and test the new settings without regenerating or recompiling the design. It even lets you perform an automatic ODT calibration that scans the available ODT settings and chooses the settings with the most margin. The VREF Margining tab analyzes the voltage margining on each I/O pin, as opposed to the calibration report that displays margining for an entire data group. For the bidirectional DQ pins, you can analyze the difference in margining between when the pin is used as an input on reads versus an output on writes. While the Calibration Report tab provides margining information based on calibration algorithm traffic from the I/O SSM, the Driver Margining tab analyzes and reports on I/O margins based on traffic from the traffic generator. Unlike the relatively simple patterns issued by the calibration algorithm, traffic from the traffic generator can be completely customized, providing a more real-world runtime view of margin on the interface. This is helpful if calibration is successful, but the interface has issues during normal operation. We'll take a look at how to customize traffic with TG2 later. The Pin Delay Settings tab lets you view the I/O delay values selected by calibration and manually adjust those delays in hardware. You can adjust both the input and output delays for bidirectional I/O. The delay settings take effect immediately, so if the settings don't match the last calibration, the tool provides an out-of-date warning. A restore option is available to return pin delays to their original calibration selected setting. Finally, if the ISSP feature of the Debug Toolkit was enabled, the ISSP tab displays several useful memory IP probes and lets you control some useful source signals, as discussed earlier. There are many sources and probes available on the tab, so here are a few highlights. For probes, you can view a count of the overall number of data reads on the interface, the number of write-read failures, and the addresses of the first data mismatch counted as a failure. the PNF probe displays the status of the pass-not-fail bits, and the TG probes indicate the status of the traffic generator's operation. Both will be discussed later. For sources, you can reset just the traffic generator with TGR, or reset the entire memory interface with resetN. Finally, you can enable worm mode, which lets you continuously read from the first failing address location indicated by the FADR probe. The final feature of the EMIF Debug Toolkit to highlight is the graphical eye viewer. The calibration report, the VREF margining report, and the driver margining report can be displayed in the eye viewer. This makes it possible to visualize the delay values tested during calibration and see what the available margin range is on each pin. Another tool you can use to help debug an interface is the all-new Traffic Generator 2.0. Let's take a look. Along with enabling the EMIF Debug Toolkit, a Traffic Generator component can be implemented as part of the interface design to issue memory access commands to the EMIF IP and the external memory. The Traffic Generator, or TG, is meant usually as a temporary replacement for the user logic that will eventually communicate with the interface. It is implemented in regular FPGA logic resources, so it can be customized for debugging purposes. Normally, and in previous versions of the memory IP, a traffic generator is automatically included when an example design is generated. The original traffic generator was configured through parameter settings, performed fixed sequences of writes and reads, and indicated whether a test passed or failed with an output status signal. Traffic Generator 2.0 allows for completely customizable pattern testing of an external memory interface during runtime. Operation of TG 2.0 can be initiated with the EMIF Debug Toolkit, as mentioned earlier. However, you can have complete control over its configuration and operation using custom debug logic connected to the IP through a standard Avalon memory mapped interface, or by using the IP's own system console-based toolkit, providing a detailed graphical interface for sending test traffic to the external memory. Note that TG2 is not available as an IP component that can be added to an existing design. To use it, it must be enabled and configured in the EMIF IP Parameter Editor so that it will get included when an example design is generated. The example design will include the new traffic generator instead of the original. The options for TG2 are found on the Diagnostics tab. Enable the use of TG2 as shown. Like the original traffic generator, TG2 can initiate a fixed default traffic pattern automatically, as well as a customized pattern. Use one or the other of the bypass options to prevent the traffic generator from initiating either of these patterns. You can't bypass both types of patterns. If you want to use the default pattern discussed in a moment, choose a test duration for the generated traffic. Choosing infinite means the default pattern will continue until the traffic generator is reset. Finally, set the TG2 configuration interface mode to either export or JTAG. Choosing export enables an Avalon slave interface on the IP to be controlled by custom logic in your design. Choosing JTAG lets you use the traffic generator configuration toolkit from the system console. We'll look at configuring and controlling the IP with the Avalon memory mapped interface first. Here are the interfaces and individual signals of the new traffic generator when the export option is selected for the configuration interface mode. The Avalon interface on the right, named Control AMM, is connected to the memory IP and is used to issue read and write commands and return read data. As recommended earlier, tapping this interface with the Signal Tap Logic Analyzer can be helpful for debugging. The data bus widths and other signal widths for this interface are set based on the EMIF width and the rate conversion option, either quarter or half rate, selected in the EMIF IP parameters. the TG status interface on the left is similar to the original traffic generator. Tap these signals with Signal Tap or connect them to LEDs for a quick indication of whether the test traffic sent to the external memory was successfully written and read back. Finally, as mentioned, TG CFG interface is used to configure and control all aspects of the traffic generator from your own custom logic. To understand how to create custom traffic patterns, it's important to understand the modes available for how the traffic generator accesses external memory locations. There are 3 addressing modes available. The sequential mode is the simplest. A starting address is selected for a write-read operation. The address is incremented by a specified value, and a test is performed at the new location. This continues until the pattern completes. In random mode, the first address accessed is a specified seed address. Subsequent addresses are pseudo-randomly calculated and guaranteed not to repeat. You can see the formula used to calculate the subsequent addresses in the EMIF IP user guide. The final mode is random sequential. In this mode, first, a specified number of sequential addresses are used, followed by pseudo-randomly generated addresses. With TG2, you can use any of these modes for your own custom traffic. Similar to the original traffic generator, TG2 can generate a default traffic pattern if the feature has not been bypassed in the parameter settings. The default pattern is issued automatically on reset of the traffic generator, or can be issued manually through the Avalon interface or the TG Toolkit. The pattern is issued in 3 stages. In the first stage, a single write-read test is performed using each of the 3 address modes. In stage 2, a block of write commands are followed by a block of read commands. This is done for each address mode. Each set of block writes followed by block reads is referred to as a loop. The number of loops performed is based on the duration setting specified earlier. In the final stage, a random Byte-Enable value is selected to write to only certain bytes at a starting address. The Byte-Enable value is then inverted so that the remainder of the bytes at the same location are written. Finally, all the bytes are read back from that location. This stage continues using the sequential addressing mode only. While the default pattern can be useful, the ability to issue completely custom traffic to the external memory is the real advantage of the new traffic generator. In order to define what traffic to send to the memory, each data bit is controlled by what's referred to as a data generator, or DG. A separate data generator is used for each DQ pin within a particular DQS group, but the patterns used for a particular DQS group are duplicated to all DQS groups in the interface. So, for example, if you have a 64-bit interface made up of by 8 groups, only 8 data generators are used to control traffic for the entire interface. There are separate Byte-Enable generators as well, but each one controls a single Byte-Enable control instead of a data line. So this example 64-bit interface would use 8 Byte-Enable generators. Each data and Byte-Enable generator can be set to one of 5 modes for pattern generation. In fixed mode, the same data is used for all traffic. The data pattern selected is referred to as a seed. In the PRBS modes, the seed is used as the starting point for subsequent pseudo-random data patterns. Each mode uses some of the least significant bits or all the bits of the seed to calculate the next pattern. See the EMIF IP user guide for the formulas used to calculate these pseudo-random binary sequences. Finally, with the rotating mode, you create a completely custom 32-bit pattern. The pattern from each data generator rotates through all the bits of the 32-bit value. See the user guide for examples of each of these modes. As mentioned, the traffic generator is configured and controlled with the TG-CFG Avalon Slave interface. This is a standard memory-mapped interface consisting of a number of control and status registers you can read and write with your own custom logic. All registers and their addresses are listed in the EMIF IP User Guide, but some of the key address, control, and status registers are listed here. To distinguish them easily, all register names are prefixed with TG. Loop count refers to the number of blocks of writes and reads performed when the traffic generator runs. Recall that for the default pattern, this was set with a parameter. For a custom pattern, you can set the loop count to whatever you want. Burst length lets you specify the length of a burst access to subsequent memory locations, as opposed to just a single access at a particular location. Sequential start address and sequential address increment let you set up the starting address and the amount to increment the address when using a sequential addressing mode. Address mode lets you set one of the addressing modes mentioned earlier. The pass, fail, PNF, first fail address, and other related registers indicate the success or failure of each pattern written to the external memory and then read back. Detailed information, such as the address location of a failure and the data pattern used, are easily accessible. And here are some of the data pattern control registers. num-data-gen lets you set the number of data generators to use. In most cases, you'll set this to the size of the DQS groups. Use num-byte-enable-gen to set the number of byte-enable generators. RDataWidth corresponds to the width of the read data and write data buses on the AMM interface to the EMIF IP, while data rate width ratio is the ratio between the AMM data bus widths and the external memory data bus. This ratio is important because it's used to determine the number of pass-not-fail, or PNF registers needed for storing the results of a test. We'll look at the PNF registers in a moment. As an example, if the EMIF is 64 bits wide and the user logic is set to run in quarter rate mode, TG RDataWidth will get set to 512 bits for a TG data rate width ratio of 8. Data seed and byte-enable seed set the 32-bit seed pattern for each generator. Finally, PPPG select and byte-enable select one of the 5 pattern modes discussed earlier for each data and byte-enable generator. The bits of the TG PNF register are the key to analyzing when and where failures occur when sending a traffic pattern to the memory. Each TG PNF bit corresponds to a data bit on the AMM interface to the EMIF IP. So with a TG RData width of 512, there would be 512 bits in TG PNF. However, the traffic generator configuration interface is fixed to 32 bits, so TG PNF is organized into as many 32-bit registers as needed for the width of the AMM interface. Thus, 512 TG PNF bits are organized into 16 indexed registers. Each TG PNF bit is simply the result of data read back from the memory XORed with its expected value, the data written out to the memory. So if a TG PNF bit is high, the correct data was read back. If it's low, the return data was different from the expected data. When a failure is first seen by the traffic generator, the address of the failure, the expected data, and the actual read back data are stored in the registers listed. TG PNF bits and these status registers are sticky, so you won't miss a failure if subsequent tests on that bit pass. Write to the TG clear register to clear just the TG PNF bits or to clear all failure status. Finally, since you can create your own custom traffic patterns, it's possible that you might configure the traffic generator in such a way that the traffic pattern itself may be the cause of data mismatches. If there is a problem with the traffic generator configuration, the TG error report register will store an error code that you can check. Check the EMIF IP user guide for a list of the error codes. As discussed earlier, you can use the ISSP tab in the EMIF Debug Toolkit to look at the value of a number of useful probes in the memory interface. Some of the information you can get from the traffic generator status registers is available here as well, so you don't have to access the information over the traffic generator configuration interface. As shown here, you can view the PNF bits along with the expected data and actual read-back data from the first failure recorded by the traffic generator. PNF bits accessed in this way are organized in groupings of 511 bits instead of the groupings of 32 bits used by the traffic generator configuration interface. So 512 bits on the AMM interface would display here a PNF0 probe of 512 bits and a PNF1 probe of 1 additional bit. Instead of creating your own custom logic to control the traffic generator's configuration interface, you can use the graphical TG configuration toolkit. To use this toolkit, make sure the TG2 configuration interface mode is set to JTAG before generating the example design. Once the example design is compiled and programmed into the device, start System Console and launch the toolkit in a similar manner to the EMIF Debug Toolkit discussed earlier. Again, see the EMIF IP user guide for details on this process. The TG configuration toolkit makes it really easy to set up and run the traffic generator. Like the EMIF Debug Toolkit, the TG Toolkit is organized into tabs for configuring a traffic pattern, and controls at the top allow you to quickly run the custom or default traffic patterns. Fields on each configuration tab correspond to the TG registers discussed earlier. So, on the Instruction Pattern tab, you can set the loop count, the burst length, and the number of writes and reads to perform in each loop. See the user guide for details on setting these and any other values. The Address Pattern tab includes all the address pattern configuration registers discussed earlier, including the address mode, along with the starting address and amount to increment for the sequential mode. You can use the same address settings for both reads and writes, or enable the separate read and write settings option at the top of the toolkit to customize reads and writes separately. You can separate read and write settings on other tabs as well. On the Data Pattern tab, select a data generator and then set its pattern mode and the starting seed pattern. The Configurations tab is an easy way to view the status registers as part of the entire register map for all the TG registers. You can export the configuration as a .csv file for future use. When a run of the traffic generator completes, the status report becomes available. In the table at the bottom, the TG PNF bits are displayed as a table. Each row represents a DQ pin. Each column represents a beat of data written out and then read back on that pin, so it's easy to see when and where failures have occurred. The information at the top of the report corresponds directly to the status registers discussed earlier. You can clear each one along with the PNF bits using the clear buttons. One final note about the memory debugging tools. If you are using the external memory interfaces for HPS Intel Agilex FPGA IP to provide a dedicated memory interface to the hard processor system in an SoC device, you cannot use any of the on-chip debugging tools discussed in this training. This special EMIF is dedicated to the HPS, so there's no way to connect the EMIF Debug Toolkit to it. However, you can use the debugging tools to test an EMIF for the HPS using a workaround. First, create an EMIF example design or a complete custom system design configuring the EMIF as you would for your HPS design, but set it up to be controlled by the traffic generator or with user logic. If you enable the Mimic HPS EMIF option on the General tab of the EMIF IP Parameter Editor, the interface will automatically be assigned to the same design elements that connect to the same dedicated I/O bank resources that are used by the HPS. Now, use the tools discussed in this training to test the design. Finally, go back to the original HPS design and configure the EMIF for HPS IP with the same parameters as the design you verified with the on-chip debugging tools. To learn how to implement this type of test design for the HPS, see Part 2 of this training, linked to in a moment. And with that, this concludes the final part of this online training. To summarize the entire training, the new EMIF architecture in the latest Intel FPGA devices was presented, and we discussed how to implement an external memory interface using this new architecture. We looked at the new features and capabilities of the architecture, especially the hard memory controller. We looked at how memory interfaces are built and how resource sharing can be used to implement multiple interfaces. We walked through the Altera EMIF FM design flow, from initial parameterization through to pin location assignments and compilation. We then looked at how to perform verification on an EMIF through simulation, timing analysis, and on-chip debug. This was the final part of the training. If you missed any of the previous 3 parts, you can register for parts 1, 2, and 3 for free at the links shown here. To learn about additional resources available to help you in implementing an external memory interface on an Intel FPGA device, continue to the next slide. There are many resources available to help you with memory interfaces in Intel Agilex devices. The documentation resources listed and linked here should be the first ones you visit. The EMIF Support Center and the EMIF IP User Guide are your one-stop shop for all things EMIF related. Besides documentation, there are many training classes available from Intel FPGA on memory interfaces, Platform Designer, and Interface Planner. The Platform Designer classes listed here will show you how to incorporate a memory interface into a complete system design. The Interface Planner online training goes through the basics of what the tool is and how it works, along with a demonstration of its use in the placement of an external memory interface. Intel FPGA provides many additional technical support resources besides technical training. Check out the online Intel FPGA forums. They're a great place to connect with other users, to share experiences, and find solutions to common issues. Visit the Intel FPGA Wiki for design examples and up-to-date articles written by field application engineers. Use the knowledge base to find solutions to the most common issues you may run into. Manage your software licenses and online training registrations using the Self-Service Licensing Center. Finally, for local assistance, contact your local Intel FPGA sales office to speak with a field applications engineer. One more thing. When you registered for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you'd fill out that survey now. We're constantly updating and improving our training materials, and your feedback helps us create the materials that you want. Thank you for your feedback. My name is Steve, and I want to thank you for taking this training on high-performance memory interfaces in Intel Agilex devices.